Hey guys, Mr. Milton here. Today we're going to look at concurrent lines. At the end of this video, you should be able to identify properties of perpendicular bisectors and angle bisectors, and you should be able to identify properties of medians and altitudes of a triangle. Okay, this is going to be a vocabulary heavy lesson, so let's start right away. Alright, so here's some vocabulary terms that we'll have to talk about. Concurrent lines. Try to switch my pen so it gets darker. Concurrent lines are three or more lines that meet at one point. Okay, the point that they meet at, called the point of concurrency. Is the point at which concurrent lines intersect. Okay, so we're going to talk about our first concurrent lines here. First, we'll go into talking about the circle that's made. A circle is circumscribed about, kind of around, circumscribed about a polygon when the vertices of the polygon are on the circle. Alright? And so here on the right side here is an example of a circumscribed circle. Circumscribed. Okay. The circumcenter of a triangle is the point of concurrency of the perpendicular bisectors of a triangle. So here we see that these lines here are perpendicular bisectors, perpendicular, cuts in half, perpendicular, cuts in half, perpendicular, cuts in half. They all meet at this point C. This is the circumcenter. Okay, that's our first center that we're talking about. Circumcenter made of the perpendicular bisectors. The point of concurrency for the perpendicular bisectors. Okay, a circle, going to the next thing, is inscribed in a polygon if the sides of the polygon are tangent to the circle. That just means that it just touches one time. So here on the right side here is an inscribed circle. Okay, we have a triangle. This circle touches just one time, doesn't go outside the circle, touches just on it once. Okay, it is made of, I guess we should talk about the center. This incenter of a triangle is the point of concurrency of the angle bisectors of the triangle. So notice that we have triangle TUV here. We have angle bisectors, angle bisector, angle bisector. They all meet at point I. I is the incenter. Okay, this is the incenter. Okay, so angle bisectors make the incenter, meet at the incenter. Okay, going next, a median of a triangle, and that is not depicted here on this front side. A median of a triangle is a segment that has its endpoints a vertex of the triangle and the midpoint of the opposite side. So here, this is a median. One endpoint on the vertex, one endpoint on the opposite side. Okay, and we'll look at this on the back, but the centroid is made up of the medians, and the centroid is also known as the center of gravity. Okay, and now we have theorems about the circumcenter and the incenter. Circumcenter is made up of perpendicular bisectors. The perpendicular bisectors of the sides of the triangle are concurrent at a point that's equidistant from the vertices. Remember, this kind of goes along with our perpendicular bisector theorem. remember, any point on a perpendicular bisector is equidistant from the endpoints of it. And so if we look at our circumcenter C, it would be equidistant from S and Q, right? Because it's on the perpendicular bisector. Same here. C is on the perpendicular bisector of QR, so it's equidistant from Q and R. So C has to be equidistant from S to Q and R. Okay? For the end center, the bisectors of the angles, so angle bisectors basically, of a triangle are concurrent at a point equidistant from the sides. Again, when we talk about that distance, we're talking about a perpendicular distance. And remember, we were saying that if a point is on an angle bisector, it has to be equidistant from the sides of the angle. So this point I is on the angle bisector of XTY, so it's equidistant from Y and X, right? The side, okay? And it's also on the angle bisector of YBZ, right? And so it's equidistant from Y and Z. So we know that it's equidistant from Y, Z, and X, equidistant from all the sides. Okay, kind of a short explanation, or at least example of how that works. Flipping to the back side, let's look at a couple more types of triangles, or triangle centers. Okay. First, we'll talk about altitude. An altitude of a triangle is the perpendicular line from a vertex to the line containing the opposite side. So in an acute triangle, the altitude happens inside of a triangle. In a right triangle, the altitude is on the triangle. Here, see how the altitude is on the triangle. No extra line needs to be drawn. And in an obtuse triangle, so here's our obtuse triangle here, the altitude is actually outside of the triangle. Okay. The orthocenter of a triangle is a point of intersection of the lines containing altitudes of the triangle. Okay. And so now let's revisit centroid a little bit and talk about its special properties. Okay, a centroid, the medians of a triangle are concurrent at a point that is 2/3 the distance from each vertex to the midpoint of the opposite side. Okay, so what that means is, for this, we should see that DC from the vertex to the centroid is 2/3 of DJ. EC, vertex to centroid, is 2/3 of EG. FC, vertex to centroid, is 2/3 of FH. So 2/3 of the whole line happens from vertex to centroid. Another way to say this is that the distance from the vertex to the centroid is always twice the distance from the midpoint to the centroid. Okay, and the orthocenter of the triangle, the line that contains the altitudes of a triangle, are concurrent. So nothing really special about the orthocenter that you can use. Orthocenter, I guess it's just kind of works that the altitudes will meet at one spot. Okay, so let's go through on the bottom here some examples of using the centroid. So down here in triangle ABC, we are going to find, they told us that DE was 6, and AH was 11. And we want to find BD. Well, remember what we said, that the distance from the vertex to the centroid is twice the distance from the midpoint to the centroid. So midpoint to centroid, E is the midpoint, D is the centroid, D, 6. So from vertex to centroid should be double that. So BD should be 12. BE then will be 12 plus 6, which is 18. Now we want to find BH. BH is a little bit different. Okay, AH is 11. We have this marked that it's going to be the same, right? Because H has to be the midpoint because that's how the median's made. So BH would be 11 as well. And AB would be 22. Just 11 plus 11. For triangle WOR, they told us that WM was 16. That RZ is 18. RZ, that's this whole line, is 18. And they want us to find each of these lengths. So MX. Well, if WM is 16, remember we said this is twice from vertex to centroid is twice from centroid to midpoint. So if this is 16, then this must mean MX is 8. Okay, if WX will be 16 plus 8, which will be 24. RZ, they told us, was 18, and so now we want to find MZ. Well, RZ, remember, it's broken down into two parts. RM will be 2/3 of 18, and this will be 1/3 of 18. So 2/3 of 18, 2/3 times 18 is 12. Did I do that right? Nope, MZ, 1/3. MZ is 1/3 of 18, which is 6, sorry. Okay, and MR is 2/3 of 18, which is 12. And we should double check to make sure that that adds up to 18, and in this case it does. Okay, so some problems there. Alright, I've got some other practice problems included in this. Make sure you take a look at those and bring those back in so we can look at those tomorrow. See ya.